Well, it is indeed a pleasure to welcome my old friend, Bill Kraushaar, and to introduce him to you today. To many of you, of course, he needs no introduction at all. Bill was a student of Ken Greisen at Cornell, and Ken Greisen, in turn, was Bruno's first American student. Bill joined the MIT faculty in 1949 and worked first with the synchrotron, and then in the air shower research that went on for a number of years. And as I remarked, in 1958, he initiated the project that discovered cosmic gamma rays, and in fact laid the foundation for one of the main scientific efforts of the United States and the European space program. In the mid-60s, he moved to the University of Wisconsin, where he built the premier X-ray group that has pioneered the exploration of the soft X-ray sky. And I remember the day when we were walking back from the F&T diner. I think we were crossing the railroad tracks, or just a hazy memory of railroad tracks. And Bill said, how about doing a gamma ray experiment on a satellite? Well, Bill went ahead and submitted a 300-pound proposal to the powers that be in Washington, which preceded the formation of NASA. A 300-pound proposal. A query came back from Washington. Can you do it for 100 pounds? Sure. And then now we're going to hear Bill Kraushaar tell us that story.
George has a remarkably generous way about him. And I'm always a little embarrassed when George... Sorry? Louder? Thank you, George, is all I meant to say. George has explained about the air shower experiment at the Agassiz station of the Harvard College Observatory. It ran for a couple of years, and there was no convincing evidence of any preferred direction of arrival. The number of events was extremely small, so the next step was design and build another experiment with a much larger area, which you heard about. Having slogged about in the snow and the mud and the mosquito environment for about 2 years, most of us were tired of that and ready for physics in a more traditional environment. A tabletop, for example. A personally redeeming feature of the physical awkwardness of the air shower experiment was the extra time I got to spend with my kids. The apparatus was located there at the Harvard College Observatory, which is in Harvard, Massachusetts. I lived in Concord, and the experiment needed adjustments and so forth quite frequently, so every Sunday morning I would go out with my kids, and I'd make adjustments on the apparatus while my kids fixed cocoa and drank it. So it was a happy time. About this time, the possibility of detecting gamma rays from celestial sources was being discussed by a few people, among them my colleagues and Phil Morrison, who at that time was at Cornell. The upper limits of a possible gamma ray component to the cosmic radiation had been set in the 40s and early 50s by, among others, Bob Holsizer and Bruno Rossi. they used ionization chambers were carried aloft by a cluster of weather balloons launched from the Lincoln Lab building out in Lexington, Massachusetts. And the idea was to search for gamma ray component of cosmic rays by searching for shower production and a few radiation lengths of lead. The balloons were made of thin rubber, which had to be boiled in water for most of the night in preparation for an early morning launch. I don't remember why you had to boil them in water, but you did. The work established a new upper limit to the gamma ray intensity above 4.5 BeV, and I believe it led to Bob Holzheiser's PhD thesis. But why look for gamma rays? Well, I had a number of reasons. One of them was a simplistic notion that it's always a good idea to look in new domains of wavelength, sensitivity, and whatnot. Another was a desperate feeling that there ought to be some kind of anisotropy associated with cosmic rays, either with their production or with their interactions. Surely cosmic ray protons and their interactions with interstellar gas ought to produce neutral pi mesons, and the decay gamma rays, if detected, would reveal the site of these collisions. This was particularly emphasized by Morrison. The other reason was to follow up on a possible embarrassment of the then trendy steady-state cosmology. Recall the idea: the large-scale features of the universe were supposed to appear the same to all observers in both space and time. Since the universe is expanding, it followed that to keep the main matter density about constant, a new matter had to be created. And if, as looked reasonable, the new matter was both matter and antimatter, the antiprotons created, at least in our galaxy, ought to annihilate and produce gamma rays in the region of 50 or 60 or 70 MeV. The availability of scintillation detectors made it possible to design a vastly improved balloon-borne gamma ray instruments. And together with Tom Klein, who was a skilled and very, very hard-working graduate student, development of a balloon-borne instrument was started, and in July of 1960, it was ready to fly. Could I have the first view graph, please? This is the Klein balloon-borne apparatus. Is there a pointer? Oh, thank you. Gamma rays were supposed to come in through the lead collimator, go through an anti-coincidence things which would reject charged particles, go into a pair converter, and get detected here in the Cherenkov counter. The upper layer of mercury was to provide a cross-section measurement because the mercury could be moved in and out, and that we hope would convince us as well as others that gamma rays were really being detected. The results, which are on the next slide, were convincing that we were looking at gamma rays at the top of the atmosphere. The intensity was very small, and then the intensity increased as you came down in height and eventually got to be very small back at sea level. This is a blow-up just of the data near the top of the atmosphere, and an extrapolation of this goes through zero. By the way, the fact that that so many gamma rays are produced in the Earth's atmosphere precludes the use of balloons to look at the collision gamma rays from outer space, because looking across the whole galaxy, the thickness is only a few milligrams per square centimeter, and the best balloon technology gets you up to a few thousand milligrams per square centimeter, so that the background problem is severe from balloons. The extrapolated intensity at the top of the atmosphere was very small here, but it was about a factor of 10 smaller than that predicted by the steady state cosmology. The steady state enthusiasts had a lot of room to maneuver, however, and I think we embarrassed them very much. It was a discovery of the 3-degree radiation in 1965, of course, that provided the fatal embarrassment. Well, it was during these years that the Russians launched Sputnik and provided a swift kick to the US satellite effort. The details of exactly what happened next are kind of fuzzy in my mind, and I look for the correspondence, and I don't seem to have very much of it. I haven't any of it. I guess it got lost in the move to Wisconsin. But we were asked to submit a proposal, and we guessed at the amount of money that was required, and how long it would take, and everything was naive about our guesses, the weight, the cost, and how long it would take. Also, they allowed us half a watt, which didn't seem very generous given the things we had to do. Well, the detector as it flew, as Explorer 11, is shown on the next slide. That's a schematic of it. The gamma rays came in through the top and got converted here in a converter, and then detected by a Cherenkov counter, and the whole thing was surrounded by a veto counter or anti-coincidence counter. And what the thing actually looked like is on the next slide. That's the detector. We made 3 of them. I think this is the one that actually flew. One of the things we had to do was to get the thing through a vibration test. And this was perfectly awful. Photomultipliers were not designed at that time to fly on apparatus going up on rackets. I recall quite vividly the first vibration test late one night in Huntsville. After the test, George Clark and I took this piece of apparatus, held it like a baby, and took it back to the laboratory, which was in a trailer. And the thing was dripping broken glass all the way back. We laid it out and looked at it and looked at the extent of the damage. And I remember asking George, well, what do we do now? And George's quite untypical remark, let's pull up a blanket and make a run for it. I think there was a culture shock for both us and the Huntsville people. I'll never forget the look of disbelief on their faces when I made some kind of a minor adjustment with a Swiss Army knife. That was not their way. Well, shortly after that, the flight into orbit was planned, and mostly because of our inexperience in dealing with hard-nosed engineers and rocket scientists, as they're called today, the orbit that we got was very, very poor. We spent 6 months in orbit and we only got 9 hours of data. The reason for that was we went up very high into the radiation belts and spent most of our time up there where the background was just enormous. So altogether, we only had, as I said, 9 hours of data. On the next slide, oh, that's the thing as it went into orbit. This is the last stage of the rocket which stayed with it. And can I have the next one, please? I've got ahead of myself. Well, forward. At the time of launch, it spun around a longitudinal axis about 5 revolutions per second. And then in a matter of a couple of weeks, the thing began to precess and eventually ended up spinning about a transverse axis. The look direction was out this way, and then as it precessed around the sky, we got a look at a large number of different directions. Including the Earth, which is on the next slide, please. This is the cosine of the angle away from the Earth, and this is the horizon, and this is the Earth that we would be looking at. The intensity coming directly from the Earth was very large because cosmic rays coming down would hit the Earth's atmosphere and produce pi mesons, which decayed into gammas, which came back up out of the atmosphere. And the region over in here was what we were getting from the sky. Well, the statistics are clearly very, very modest. We did not have a convincing demonstration, I don't think, that we were detecting gamma rays. But a couple of years later, we were given the opportunity to prepare an instrument for the third orbiting solar observatory, OSO 3. That's on the next slide. And the main improvements were the inclusion of a kind of a calorimeter in here where we could measure the energy of gamma rays, although quite poorly, and the fact that the orbit of this was much, much more to our liking. On the next slide is the results again, and this would be towards the Earth, and this would be towards the horizon, and this is looking out into the unobscured sky. And it was a more convincing case that we were detecting gamma rays out here at a level which was reasonable. On the next slide is shown the distribution with galactic latitude. This is the galactic plane, and this would be the North Galactic Pole. This would be the South Galactic Pole, and there clearly is a high intensity towards the galactic plane, here, 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 and so forth. I'm sorry, I said that wrong. This is the galactic plane going back and forth this way, and these are the poles. Yes, I was right. The problem with these measurements in general was that the angular resolution was so extraordinarily poor. And the reason for that is that you have to convert the gamma rays into electron-positron pairs, and this requires a converter, but the converter is very effective in scattering the electrons. So we were limited to do something like 15 or 20 degrees for the angular resolution of the device. Things that occurred later than this were usually done with spark chambers, and one of those is shown schematically on the next slide. This is a device which is called a COS-B, which was prepared by the Europeans, And as you see, it contains a spark chamber up here with a whole bunch of thin plates. And this let the gamma ray get detected in one of the plates. And then you'd get a look at the electrons that were produced before there'd be a lot of scattering. On the next view graph is shown the distribution about the galactic plane from from SAS-2, which was a NASA thing. And on the next one is from COS-B, is a map of the galactic plane, which goes through here, and the intensity gets smaller and smaller and smaller as you go up towards higher galactic latitudes. And there's an enormous amount of detail. Not all of it is significant, but a lot of it is, and it indicates directions by and large in which there's a concentration of gas, such as molecular clouds. So the gamma rays can be used as a probe of concentrations of gas. I'd like to add a couple of things here. Bruno Rossi, Gerald Zacharias, Peter Demas, Fred Epling, and Herb Bridge all supplied an enormous amount of logistic and administrative support for the efforts that George has talked about in these. And they are the fact that we didn't have to go after funds, it didn't have to write proposals for our day-to-day activity was a tremendous advantage that I think we all thoroughly appreciate. In addition to that kind of support was the support of the technical people. Cy Turtelot, Bill Smith, Ed Mangan are all people who were tremendously devoted and added an awful lot to the possibility of success in these things. None of the three of us, Clark or Garmeyer or me, have pursued gamma ray astronomy beyond OSO 3. Speaking for me alone, there was a number of reasons. Too much travel, too many meetings, too long between experiments, too hard to provide students with hands-on or a tabletop experience in experimental physics. These later things were done by large groups, both at NASA, Europeans, and most recently the Gamma Ray Observatory. My last slide is of GRO, and I guess my only comment about it is things can get very complicated if you don't watch out. It's not a tabletop thing, and I don't see how you fit graduate students into it very gracefully. Well, thank you all, and thank you for listening.